In this presentation, I am going to explain the questions and answers for the year 2024, and the topic that is covered is power electronics. Now let us see the first question, that is a 2024 gate question that carries 1 mark. A single phase time-based AC voltage controller feeds RL load. The input AC supply is 230 volt 50 Hz and the value of resistance R and L are 10 ohm and 18.37 millihenry. The minimum triggering angle of the track to obtain the control output voltage is, the options are A 30 degree, B equal to 60 degree, C equal to 45 degree and D equal to 15 degree. Therefore, the minimum firing angle of track is to be found out. Now come to this is the circuit diagram of a single phase AC voltage controller, and here the voltage, that is the input voltage, equal to 230 volt 50 Hz, and here this is a track and this is the RL load that is connected. Now the minimum value of the track, that is minimum value of the firing angle of the track, that can be calculated by calculating the power factor angle. Therefore, the minimum firing angle of the track is the power factor angle of the load. For the reduction of alpha or firing angle below the power factor angle phi is not able to control the load voltage and the load current. It's not possible. If the firing angle is less than the power factor angle of the load, that cannot be controlled. Therefore, thus the AC output can be controlled only when the firing angle is more than the power factor angle. Therefore, the minimum firing angle is the power factor angle. Therefore, you have to calculate what is the power factor angle. Therefore, that the triggering angle alpha can be same as the power factor, the minimum power factor or the minimum firing angle can be same as the power factor of this circuit, and that power factor of the circuit can be calculated. It is equal to tan inverse XL by R. XL equal to 2 pi F into L or omega L divided by R, which is equal to tan inverse 2 pi FL into R. 2 pi 50 into 18.37 into 10 raised to minus 3 divided by the resistance 10 ohm, and we'll be getting tan inverse 0.5771, or corresponding the firing angle is equal to, we'll be getting, or this is actually power factor angle. Power factor angle will be getting, it is equal to 30 degree, and which is the minimum value of the firing angle. Therefore, the minimum value of the triggering angle is equal to 30 degree, and the answer is the option A. Now let us see the second question of 2024 gate question, that's also 1 mark. If the following switching devices have similar power rating, which one of the same is the fastest? The first one, GTO, gate turn off switch, and power MOSFET, then IGBT and SCR. These are the switching devices in which one is having the it is the fastest for the same power rating, and these characteristics are given here as such. MOSFET high frequency and that's medium, and IGBT is the high speed and high power, and BJT is capable of handling high current and voltage. It has a slower switching speed, and thyristor is high power and lower switching speed. Therefore, these are the characteristics of different switching device. Looking into that one, we can see that the MOSFET, which is having a high frequency and medium power application, that can be used. Therefore, the answer is power MOSFET. That is, answer is option B. Now let us see the third question that also carries 1 mark. A force commutated thyristorized step down chopper is shown in the figure. This is a step down chopper. Neglect the on-stage drop across the power devices. Assume that the capacitor initially charged to 50 volt. Initially this capacitor is being charged to 50 volts with a plus here and minus here, with a polarity shown in the figure. The load current IL can be assumed to be constant. The current through the load is, we are assuming it is equal to 10 ampere. Initially, the thyristor, this is called the main thyristor and this is called the auxiliary thyristor. The main thyristor is on and auxiliary thyristor is off. This is on and this is off. The turn off time available to, that is a main thyristor. What is the turn off time available for the main thyristor in microseconds when the auxiliary thyristor is triggered? That is the time. That is normally here, in order to turn off this main thyristor, we'll be triggering on this one, on the auxiliary thyristor. so that here a reverse voltage will be appearing across the, because this will be conduct, this is when this is on here, therefore this polarity comes across that one, that will be reverse biasing the thyristor, which is already main thyristor, that is getting turned off. Therefore this auxiliary thyristor, as and when auxiliary thyristor is turned on, a reverse voltage will be applied to the main thyristor. That is the way in which it is being commuted. And here, in order to find out the turn off time available to this main thyristor, the basic equation is that IC, that is current through the capacitor, when that is this path, through this path as such here, when this is coming, actually this is current is flowing in this path, because as the thyristor, and so that negative comes here, the current is flowing in this direction. And the current equation C equal to dV by dt for the constant load current, because this is, even when this is switched off, that it's supplying a constant load current. For a constant load current I0, the relation I0 equal to C into Vs divided by Tc, or Tc is the time of turn off time as such, or that is equal to C into, that is, what is this voltage, because this is being charged to the same as the supply voltage, 50 volt. C into, that is 10 into 10 raised to minus 6, 10 microfarad into 50 divided by, what is that load current, 10 amperes, or that 10 ampere, or that's equal to 50 microsecond. Or this is the turn off time of the main thyristor. As and when it is turned on, it takes that much time, that is 50 microsecond to turn off the turn off time of this main thyristor. Therefore, the auxiliary thyristor is used to turn off this main thyristor. Therefore, that basic equation is that one, Tc equal to C into Vs divided by I0, where Vs is the voltage, that is input voltage, is same as the capacitor charge voltage, that divided by the constant load current. So that's equal to 50 microsecond. Now let us see the fourth problem, 2024 gate question that carries 2 marks. Single phase half control bridge rectifier, that is a single phase half control bridge rectifier. Here these are the two thyristors and these are the diode. Therefore single phase half bridge rectifier, it supplies the inductive load with a constant current, is supplying an inductive load with a constant current, load current is equal to constant, and the firing angle alpha value is 60 degree. It is the firing angle equal to 60 degrees, the firing angle. Ratio, now question is ratio of RMS value of the fundamental component of current to the total current RMS value. For the total current RMS value, that is fundamental component of the, RMS value of the fundamental component divided by the RMS value of the total current. That is question is that one. Therefore, this is the circuit diagram in which the single phase supply is given. These are two thyristors, and here T1 and T2, and D1 and D2 are the diodes. Now this is the load that produces a constant load current, and this is, and if you see that one, the firing angle equals say 60 degree. This is the input voltage, and the output voltage is this one. That is you will getting output voltage from alpha to pi, Then from pi to pi plus alpha, there is no voltage because none of the thyristor is. Of course, this is short circuited and zero voltage is there. Therefore, it's a freewheeling action is taking place. Therefore, the output voltage will be zero. The device that are conducting, it is marked here. That is when T2 and D1 are conducting, you will be getting zero voltage. Similarly, when T1 and D2 are conducting, you will be getting zero output voltage. That is during the freewheeling action, and this is the voltage that is available across the load. And output current is constant. Load current is assumed, and that is constant. Therefore, if you look into the input current, you can see that one, that from alpha to pi, current will be positive. Here zero current. Again, from pi plus alpha to 2 pi, there will be negative current. Therefore, this is the current waveform at the input side. That is the side shown here. Alpha 2 pi plus I0, and pi plus alpha to 2 pi minus I0. Therefore, this is the current at the input side. The question is that what is the RMS value of the fundamental, and to that ratio to the RMS value of the total current, that is to be found out. For that one, if you do the Fourier analysis of the current, that is the current waveform is not sinusoidal, it is a square wave. That is here it is, we can say that one, it is from alpha to pi, you are getting a plus I0, and from pi plus alpha to 2 pi minus I0. Therefore, this is the current waveform. We have to do the Fourier analysis of this one, As you know that A naught plus sigma n to 1 to infinity n cos n omega t plus bn sin omega t, where the constant that A naught here, this is as a property like it is called half-wave symmetry. Half-wave symmetry means ft equal to minus of ft plus t by 2. If you satisfy this one, this is called half-wave symmetry. Therefore, if you have a half-wave symmetry here, the constant, the DC component, that is A naught equal to 0, and another one A1 and B1, you can calculate what is the constant A1, the fundamental component of a coefficient An, and corresponding fundamental component Bn, or A1 and B1 can be calculated. That is 4 by 2 pi integral alpha to pi, which is equal to I naught cos omega t d omega t. This is equal to A1, the Fourier constant corresponding to the fundamental A1. And this corresponding the Fourier will be getting 2 minus 2 I naught divided by pi into sin alpha. Similarly, B1, the constant B1 corresponding to the fundamental, it is equal to 4 by 2 pi integral alpha 2 pi, that is integral alpha 2 pi I naught sin omega t d omega t, or it is equal to 2 I naught by pi into 1 plus cos alpha. The first step is you are calculating A1 and B1. Once you can get A1 and B1, the maximum value of the fundamental is given by root of A1 square plus B1 square. Then once you get maximum value of the fundamental, RMS value of the fundamental is given by root of A1 square plus B1 square divided by root 2. Therefore, here first we are calculating root of A1 square plus B1 square. That is A1 is the A1 square plus B1 square. Then that is you will be getting, it is equal to 4 I naught divided by cos alpha by 2. This is the maximum value of the fundamental. That is the maximum value of the fundamental 4 I naught divided by pi into cos alpha by 2. And the RMS value is given by that divided by root 2. We'll see in the next slide. So for continuing same problem here, RMS value of the fundamental is calculated. That is IS1, RMS value of the fundamental source current, which is equal to root of A1 square plus B1 square, that is maximum value, that divided by root 2, or 2 root 2 I naught divided by pi into cos alpha by 2. This is the equation, RMS value of the fundamental. Similarly, the RMS value, total RMS value, what is the RMS value of the total waveform as such? That is equal to square root of 1 by pi integral alpha 2 pi I naught square d omega t, or I naught into root of pi minus alpha divided by pi. Therefore, this is the RMS value of the total waveform, and this is the RMS value of the fundamental. The question is that what is the ratio of the RMS value of the fundamental to the RMS value of the totals? Or if you take the ratio here, that is RMS value of the fundamental to the RMS value of that is actually distortion factor, and that is equal to, we will be getting it is equal to 2 root 2 divided by root 2 pi into pi minus alpha into cos alpha by 2. We are taking this ratio, and when corresponding to alpha equal to 60 degree, we are given alpha equal to 60 degree, you can calculate what this is also called distortion factor, which is equal to IS1 divided by IS. It is equal to, because if you substitute that one, you will be getting it is equal to 0.955. The answer is 0.955. Now, in order to remember this one, and rather than deriving this one, you just remember that one. RMS value of the fundamental equal to this equation, you remember 2 root 2 by pi I naught cos alpha by 2, corresponding to firing angle alpha in a semi converter, and here semi controlled rectifier as such. Therefore, RMS value of the total source current, RMS value is where you remember just this one only, I naught into root of pi minus alpha divided by pi. Therefore, you just remember this one and this one, and of course the ratio you can take that one, that will be getting the ratio of the IS1 divided by IS. Therefore, this is the equations to be remembered, and the final equation for this one is equal to the distortion factor, or the ratio of the fundamental RMS value to the total RMS value, IS1 divided by IS, equal to 0.955. Now, next problem, that is problem 5, that is 2024 gate question, that also carry 2 marks. In the DC to DC converter shown in the figure, that is given in the figure, the current through the inductor is continuous. Current through the inductor is continuous, and the switching frequency is 500 Hz. The voltage V0 across the load, that is the voltage across the load V0, is assumed to be constant and ripple free. The peak inductor current in ampere is this, that is to be rounded off to the nearest integer. That is the question. For the circuit diagram is given here. Therefore, the circuit diagram is a boost converter, and in which the input voltage equal to 20 volt, and across the load the voltage is equal to 40 volts. Therefore, in continuous conduction mode, the voltage average output voltage, that is V0 divided by the Vs, equal to 1 by 1 minus D for a boost converter, where D is called the duty cycle or duty ratio, which is equal to on period divided by the total time period, T on divided by Ts. Therefore, V0 by Vs is given by 40 divided by 20 equal to 1 by 1 minus D. From this equation, we can find out what is the duty cycle is equal to 0.5. Therefore, the duty cycle of this switch is equal to 0.5. Now, once you get 0.5 in duty cycle, as you know that when the switching frequency is equal to 500 hertz. Therefore, switching time period can be calculated as Ts equal to 1 by Fs or 1 by 500. 1 by 500, that becomes 2 milliseconds. So the switching time period equal, that is the total switching time period is equal to 2 milliseconds, and the duty ratio in this, it's not 50, here duty ratio is given as 50%. Therefore, in that case, we can, of course, the on period, the duty cycle is given by on period divided by total time period Ts. Therefore, the on period can be calculated as the duty ratio into the switching time period. So that is equal to 0.5 into 2 into 10 raised to minus 3, or that equal to 1 milliseconds. Therefore, here on period equal to 1 millisecond, and of course the off period is also equal to 1 millisecond, 50% duty ratio. Now, the voltage across the inductor, that during the on period, as you know that one, the voltage across the inductor is same as the input voltage. When switch is on, the voltage across the inductor is same as the input voltage. Therefore, that is here VL equal to, basic equation is VL equal to L di by dt, or here L into the change in inductor current divided by the duration of the on period is given by T on. Therefore, the change in inductor current is given by, but how during that period, on period, delta IL is given by, what is that, VL divided by L into T on, VL divided by L into T on. Therefore, VL is nothing but the input voltage 20 divided by the inductance value is given as, of course, that is equal to 2 millihenry. Therefore, 2 into 10 raised to minus 3 into the on period we calculate is equal to 1 millisecond, or we will be getting 10 amperes. Therefore, the peak to peak value, that is delta IL, is equal to, we got it as 10 amperes. Now, in order to find out the peak value of the inductor current, we have to add the average value of this one, that is here, this is called the source current plus delta IL by 2. This is the input current, that is the current at the input side is equal to this one. Therefore, the average value of the input current or source current, that is source current, that plus delta IL by 2 is the peak value of the current, inductor current. Therefore, in order to find out the average value of this source current, the basic relation between output current and input current, that is I0 by Is, that is equal to 1 minus D. Here V0 by Vs equal to 1 by 1 minus D, and I0 by S equal to 1 minus D. That's a basic relation like that one. Therefore, I0 by Is equal to 1 minus D, or from this one you can find out what is the source current. That is average source current equal to average output current divided by 1 minus D. Average output current to find out, average voltage equal to 40, and this is equal to 10 ohm. For 40 divided by 10 ohm, that's equal to 4 amperes. Therefore, 4 amperes is the average output current. Therefore, the input current is given by 4 divided by 1 minus 0.5, or 1 minus D 0.5, which is equal to 8 amperes. Therefore, the average value of the source current is equal to 8 amperes, and delta IL is already calculated as it is equal to 10 amperes. Therefore, this average current plus delta IL by 2, that is, it is equal to 8 amperes, that is source current plus half of this delta IL or delta IL by 2, which is equal to 10 by 2, which is equal to 13 amperes. If the peak value of the inductor current at the input of the boost converter is equal to 13 amperes. Now let us see the sixth problem, 2024 gate question, that also carries 2 marks. A single phase full control thyristor converter bridge is used for the regenerative braking of a separately excited DC motor with the following specification. Specification is rated armature voltage of this machine is 210, rated armature current equal to 10 amperes, and rated speed equal to 1200 rpm, armature resistance equal to 1 ohm, and input to the converter bridge, that is here this converter bridge, it is equal to 240 volt 50 hertz supply, and the armature of the DC motor is fed from the full converter bridge, and the field current is kept constant. It's a separately excited motor. This is the circuit diagram. Assume that the motor is running at 600 RPM and the armature terminals of the motors are suitably reversed for regenerative braking. If the armature current of the motor is to be maintained at the rated value, that is 10 amperes, the triggering angle of the converter bridge in degrees should be what is rounded to 2 decimal. What should be the triggering angle of this one during the regenerative braking condition in which the motor is running at starting as 600 RPM. Now let us see the solution as such. Now for that, for a separately or say DC motor, the back EMF basic equation for the back EMF is given by EB equal to phi Zn divided by 60 into phi by A. You know that equation. For phi Zn, n I can replace by it is equal to omega m equal to 2 pi n by 60, or n can be replaced by 60 into omega m divided by 2 pi. Now substituting that one here, we'll be getting Pz divided by 2 pi A into phi into omega m. So these are all constant. As far as a machine concerned, this is a constant Pz divided by 2 pi A, or that is equal to a constant Ke into phi into omega m, where Ke equal to Pz divided by 2 pi A. That's called the motor constant. Therefore, basic equation is that the back EMF EB equal to Ke into phi into omega m. Now, for a separately excited motor, as you know that flux is a constant. The product phi into Ke is another constant that is represented by a constant K. That is K into omega m. Therefore, the back EMF can be written as EB equal to a constant K into, which is equal to K into omega m. For omega m means, as you know that it is equal to 2 pi n by 60. Now continuing the same problem, this is during motoring action, the power is flowing from AC source into the motor, or electrical power is converted into mechanical power. That's called the motoring operation. During the motoring operation, the voltage, that is what we are applying, this voltage is the voltage that is applied across the motor. For that DC voltage that is applied across the armature, that is equal to the back EMF plus the drop across the armature resistance, or IA into R. Or here, that is 210. The writing of the motor is given as 210. 210 equal to that EB already found the equation, no? K into 2 pi. It is running at 1000. The rated speed is equal to 1200. Therefore, 1200 divided by 60. Therefore, that into that plus the rated current equal to 10 amperes. Armature resistance equal to 1 ohm. Now, from this equation, we can find out what is this constant. That idea is to first find out this motor constant K. For V equal to, from the rating of the motor, we are finding out what is the constant K. Therefore, we will be finding out K equal to, it is equal to, substituting here, we will be getting 1.59 volt then second per radians. Therefore, this is the constant of the machine. Now we are coming to the regenerative braking condition. Regenerative braking condition, what happens here? Here, during regenerative braking condition, the terminals are being reversed. Previously, A was here and A was here. Now it is AA and A here. It is reversed. And in that case, the basic equation will become the supply voltage equal to minus EB plus IARA. Minus EB plus IARA, because the polarity is reversed here. The power is flowing from, that is from the DC source into the, for the motor, into the AC, or the mechanical power is converted into electrical power. The power flow is in this direction, and the basic equation when during the regenerative braking is given by the voltage V, that is this voltage is equal to minus of back EMF plus IARA, or minus of K into, since it is running at 600 RPM during the regenerative braking, minus K into 2 pi into 600 divided by 60 plus same current we are considering 10 into 1 ohm. Or from this equation, we can calculate what is EV, the voltage that is to be applied here, equal to minus 89.9 voltage. That is, for during the regenerative braking condition here, the polarity of this voltage, of course, negative, and that magnitude is equal to 89.9 volts. That is, here the voltage should be equal to minus 89.9 volts. Now the question is that what should be the firing angle of this converter? The basic equation to the input voltage and the DC output voltage is, it is equal to a single phase 2 Vm by pi cos alpha. The average voltage in a single phase controlled rectifier, the average voltage at the output is given by 2 Vm by pi cos alpha. Therefore, 2 Vm by pi cos alpha should be equal to minus 89.9 volts, or from 2 into here 240 volt is the RMS value. Root 2 into 240 divided by pi into cos alpha equal to minus 89.9, or cos alpha equal to minus 0.416, or alpha equal to cos inverse of this value, or we'll be getting the firing angle equal to 114.58 degree. Therefore, this converter should operate with a firing angle of 114.58 degrees, so that this motor is working in a regenerative fashion, or the power flow is from the DC side into AC. That's called the regenerative braking. And during that period, the speed what we select is given as 600 RPM, as well as the current is same as the previous rated current, 10 amperes. So the answer is 114.58 degrees. That is the firing angle of the converter. Now let us see the seventh problem. That is 2024 gate questions, 2 marks itself. It is a single phase full bridge voltage source inverter feeds a purely inductive load. This is a voltage source inverter that is feeding a purely inductive load. The inverter output voltage is a square waveform. The voltage inverter output voltage is a square waveform. The fundamental frequency of the output voltage is 50 Hz. This fundamental frequency is 50 Hz, means this is equal to 10 milliseconds, and this is equal to, again up to this one it's a 20 millisecond. Total frequency is equal to 50 Hz. And if the DC input voltage of the inverter is 100 volts, this voltage is equal to 100 volt. Value of the 100 volt, and the value of the load inductance is 20 millihenry. The peak to peak load current in ampere is round off to the nearest integer. What is the peak to peak current of the inductor? That is current through the inductor. Now here, when switch is on, as you know that one, here will become plus and here will become minus, because when switch this one is on, here path is like this one, T1 and say T2, or if I even diode also conducting that same thing. Therefore, that during that period you will be getting a positive voltage, and when other two thyristor T3 and T4 are conducting, you will be getting a negative voltage. Therefore, this is the output voltage or voltage across the inductor. And as you know, the relation between the voltage across the inductor and of course the current through the inductor is equal to VL equal to L di by dt. VL equal to L di by dt, or di by dt equal to VL by L, or di equal to VL by L into dt. The rate of change of current through the inductor equal to VL by L into di. Therefore, here in this case the frequency is 50 Hz. Therefore, the time period is equal to 1 by 50, which is equal to 20 milliseconds. This is equal to 20 milliseconds. Therefore, during on period, we can say that during high period, that is when T1 and T2 are conducting, you can see this is equal to 10 milliseconds. Therefore, during the 10 millisecond, what is the change in current? Because the voltage here, it is equal to same as 100, because when T1 and T2 are conducting, the voltage across the inductor is same as the supply voltage 100. For 100 voltage is supplied here, and inductance value equal to 20 millihenry. Now the question is that what is the change in current during this 10 millisecond? Therefore, that is can be calculated as during 10 millisecond VL by L into that much half of the time period T by 2, or VL equal to 100 divided by 20 millihenry, that into this duration, that is during the high period, that is equal to 10 millisecond, which is equal to 50 amperes. Therefore, here the total change here it is equal to 50 amperes, or again the change in current is from minus 25 amperes to the plus 25 amperes. And therefore, the peak to peak current, the question is that what is the peak to peak current of the inductor? That is because here the change in current equal to, we are calculated, it is equal to 50 amperes. Therefore, the current is changing from minus 25 amperes to the plus 25 amperes. Therefore, peak to peak current through the inductor is equal to 50 amperes.